We're going to look at two methods for solving each of these problems. The first problem is the commission earned on a sale varies directly with the price of the item sold. If the commission earned on a $26 item is $6.24, what is the price of an item when the commission earned on the item is $38.88? The two things we're comparing here are commission and price. So let's use C for commission and P for price. Since they vary directly with each other, we can say that commission is some constant of variation times the price. Now we're told that the commission is $26 when the price is $6.24. So that means that 26 equals K times $6.24. If we divide both sides of the equation by $6.24, we can solve for the value of that constant of variation K. So the value of K in this case is 0.24. Now we'll go back up to our equation, C equals K times P, and since we know what K is, we'll substitute the value of K in for the K, and we have C equals 0.24 times P. We want to know the price when the commission is $38.88, so we can substitute $38.88 for the C, and we can get an equation with only P in it that we can solve by dividing both sides of the equation by 0.24. And we end up with P equals 162. So the price of the item was $162. The second method we can use is to write a proportion that compares the commission with the price. We're going to need two fractions that both compare commission and price in that same order. The first sentence says that the commission earned on a $26 item, so that's a price, is $6.24. That's a commission. We want to know the price when the commission on an item is $38.88. So now that we've got a proportion, we can cross multiply to solve. So $6.24 times the X equals 26 times the 38.88. So 6.24 times X equals 1,010.88. And if we divide by the 6.24 on both sides, we'll find that X equals 162. So once again, we know that the price of the item was $162. Now this one is also a direct variation problem, but it's got a little bit of a twist to it. It says the distance a body falls from rest varies directly as the square of the time it falls. If a ball falls 144 feet in 3 seconds, how far will the ball fall in 7 seconds? So we're going to try the same two methods, but we have to be careful because it doesn't say it varies directly as the time, it says the square of the time. So we'll have to take that into account. So let's write our equation first. We'll use D for distance. So the distance that a body falls varies directly as the square of the time. So not just the time, the square of the time. The ball falls 144 feet, so that's a distance, in 3 seconds. So T is 3, but we have to square that. So now we can solve for that constant of variation K. So 144 equals K times 9. Divide by 9 on both sides, and we get K equals 16. So now that we know our constant of variation, we'll rewrite the equation. The distance is 16 times the time squared. And we want to know the distance that the ball will fall after 7 seconds of time. So D equals 16 times 7 squared is 49. So D is 784, and we are measuring this in feet, so that would be feet. To solve this with proportions, we're going to have to be careful about the time again, because the time is squared in this problem. So we're going to compare distance and time, but because it says the distance varies directly as the square of the time, we are going to have to square the time in each of our fractions. So we'll be comparing distance and time squared. So for the first fraction, a ball falls 144 feet, that's a distance. In 3 seconds, that's a time, we have to square it. For our second fraction, we want to know how far the ball will fall, that's our distance, in 7 seconds. So we have to square the 7. So now we can solve this proportion. We're going to have to do the squaring, so let's do that first. So 144 over 9 equals x over 49. If we cross multiply, we get 9x equals 49 times 144. 49 times 144 is 7,056. And then if we divide both sides by the 9, we get x equals, once again, 784, and this is feet. The next problem is an inverse variation problem, which we will once again solve with 2 methods. The time it takes you to get to campus varies inversely as your driving speed. Averaging 20 miles per hour in bad traffic, it takes you 1.5 hours to get to campus. How long would the trip take averaging 50 miles per hour? So if we solve this using an equation and look for the constant of variation, we'll have to think about what we're comparing. In this case, it's time and speed. So let's use T for time, and we'll use S for speed. So our time is some constant of variation, not times the speed, but divided by the speed, because this is an inverse relationship. So if we average 20 miles per hour, that's a speed. When it takes us 1.5 hours, we've got 1.5 equals k times 20. If we multiply both sides of this equation by 20, we get k equals 30. Now that we know what the constant of variation is, we'll rewrite our equation as t equals 30 over s. And what we want to know is how long the trip would take. So we want to know the time when we average a speed of 50 miles per hour. So t equals 30 divided by 50, which simplifies to 3/5, and our time is in hours, so it's 3/5 of an hour. Now let's do the same problem with a proportion. Because this is an inverse relationship, we're going to have to set it up slightly differently than the direct variation. We're still deciding what we're comparing. In this case, it's time and speed. So we're going to pick an order here for our ratios. So let's compare time and speed. We'll compare in that same order in both ratios. So now let's figure out where our values are going to go in our ratios. So we know that we average 20 miles per hour and it takes us 1.5 hours. So 1.5 hours, that's a time. We'll put that in the numerator of the first fraction. But the speed that corresponds to that is 20 miles per hour. Now if this were a direct variation problem, we'd put that 20 right underneath the 1.5. But because it's inverse variation, the 20, which is a speed, is going to go in the denominator of the other fraction. And we want to know how long it would take, so we want to know a time when we average 50 miles per hour. Now the setup's the tricky part. Now it's easy. We just cross multiply. So we get 50x equals 1.5 times 20. So 50x equals 30. Divide both sides by the 50. And once again, we get x equals 3/5 of an hour. Our last problem is an inverse variation problem, but this one has a little bit of a twist. The weight of an object above the surface of the Earth varies inversely with the square of the distance from the center of the Earth. If a body weighs 50 pounds when it is 3,960 miles from the Earth's center, what would it weigh if it were 3,970 miles from the Earth's center? So let's write our equation first. We'll try that method to begin with. So we know that the weight varies inversely, which means the next quantity is going to go in the denominator, inversely with not just the distance, but with the square of the distance. That's the twist here. So now that we've got our equation, let's substitute some values in to find the value of k. So if a body weighs 50 pounds, when it is 3,960 miles from the Earth's center, don't forget that has to be squared because our distance is squared. So now we're going to multiply both sides of this equation by the 3,960 squared to find the value of k. So k is 784,080,000. So now let's finish up the problem knowing what the value of k is. 784,080,000 divided by, remember, not just d, but d squared. And we want to know what the weight is when the distance is 3,970. That has to be squared. So the weight does not come out to be a pretty number. It's a decimal number. Let's just take it to 3 decimal places. So it's 49.748. And the weight was in pounds. So this is pounds. Now let's try the same problem, but using proportions. So we're comparing two things here, weight and distance. But it's not just distance, it's square of the distance. So in each fraction we write, we'll compare those two things, weight and square of the distance, in that order. Now here's the thing we have to be careful of. This one's inverse variation, so we have to be careful about the order we put things in our fractions. It says a body weighs 50 pounds, so we'll put that in the numerator of the first fraction. When it's 3,960 miles from the Earth's center. Now, if this were direct variation, we would put that 3,960 in the denominator right underneath the 50. But because it's inverse variation, that number, 3,960, which remember we have to square, is in the other denominator. And we want to know what would it weigh if it were 3,970, which we have to square, miles from the Earth's center. Okay, so our numbers are a little big here. Rather than squaring them right now, let me just leave them like they are and cross multiply. So we would say that 3,970 squared times x equals 50 times 3,960 squared. And if we divide both sides by the 3,970 squared, we'll be able to solve for the x. And once again, we get that weird decimal that repeats, but if we take that out to 3 decimal places, we get about 149.748. And remember our weight was in pounds, so this would be pounds.